Thanks for coming for the session. So we are presenting our paper called Detection of Objects and Trajectories in Real Time Using Deep Learning by Controlled Robot. The authors of the papers are Adil Sarsenov, Aygirim Yesinbayeva, which is myself, Almaz Shantimirov, and Adnan Yazici. And we were working on this paper at Nazarbayev University. So let me start with the motivations of this project. So we know that currently in nowadays that robotics and machine learning are one of the trending areas, and combination of this gives us the opportunity to work robots autonomously. And so if I'll zoom my poster, which I have for today, this is our objectives. Sorry about this. Mobile robots also are one of the useful thing of robots is that they can collect different heterogeneous informations, and they can perform it basically at technological at any technological operations in extreme environment. So every robot definitely needs some input sensors, and for our project, the sensors which we used are HOQ LiDAR, 2D HOQ LiDAR, IP camera, depth camera, Raspberry Pi, and Jaguar 4x4 wheeled mobile robotic platform. So there is a picture how we build it, and the LiDAR commenter was set up at the very top of the robot. So it had some advantages that it cannot see what is below that. However, it's still perfectly fine with defining the, with estimating the distance and even trajectory. So methods and the data sets. In order to work on our project, we used deep learning algorithms, and we compared initially with CNN algorithm for image processing. However, it takes different fragments of the image and then tries to determine the object there, so and classify. However, this process is very slow, and faster RCNN is performing a little bit better because it's instead of taking every fragment of the image, it's basically predicting the object itself. So YOLO-V3 is even faster because YOLO-V3 is using the pre-trained weights, and can give object detection with high speed. So this process is called transfer learning, and that's the one which we used in YOLO-V3. So in order to determine even the object, there is always a bounding box where the object is located with some coordinates. So we used also different variety of algorithms how to determine the coordinates. Either it starts from the center of the image or just gives an angles of that bounding box, or sometimes even just x and y coordinates and the height and width of that bounding box. So that's about the algorithms which were used for image processing, basically determining the object. For trajectory estimation, we use different sensors, as we described a little bit earlier. So one of them is LiDAR, depth camera. We also used LRF which is laser rangefinder, and we used CMOS for comparisons, which is complementary metal oxide semiconductor camera. And for determining the distance and trajectory measurements, we did different combinations of different cameras in order to make sure that each of them is working correctly. As for determining the distance, we could use simple laser or radars, and therefore we can use LRF as the ground truth for comparison with, for instance, depth camera, in order to check how the depth camera is working. We also did the comparison of depth camera with LiDAR, and comparing there, obtaining the distance from depth camera and the angle from LiDAR. So that's a different combinations how we were trying to check, and using also different scores like RMC, which root means square error. Also we used R squared, polynomial degree, and Spearman correlation scores. We will come to that a little bit later. So for the data sets, we used Google Open Images v4, Pascal WOC 2007, and WOC 2012. ImageNet as a backbone was used for each experiments as well. So our steps for the whole project was mostly that we used transfer learning, which is using pre-trained weights inside of our YOLO v3 algorithm, which actually detects and recognizes objects. And if the object is recognized, we save it in we save the coordinates of that, which we mentioned earlier, in CSV file. We also plot the scatter plot of all these coordinates, and then we use a polynomial regression, which smoothes our trajectory path to the object. So we can all see this here in experiments and result. So the first table, which shows different results for CMOS, CMOS, depth camera, and 2D LiDAR. So AD is the actual distance. So we used 4 different experiments with object located in 275 meters from the camera, or 5.5 meters, or 7.25 meters, or 9 meters from the camera. So the measured distances are here for the CMOS camera, for the depth camera, and LiDAR camera. We also can see the errors which we're having for different cameras. As you can see, for LiDAR we have 0 errors, which is very perfectly determines the distance for the object. Depth camera can be used with the closer distances. It determines more precise, much better. But with getting bigger distance from the camera, it's getting a little bit worse with determining the distance. And with the CMOS camera, it's pretty much similar despite what the distance it is. So CMOS has little error, not that big, and still it's a more constant, I would say. Polynomial regression, as I mentioned earlier, used for fitting our scattered coordinates received from the cameras, and it's represented in these images. There are 4 different passes, and in the next table, based on that figure 6, we can see that here the figures A, B, and C, D, which are presented here, they have measured with different scores: RMC, root mean square error, R squared, and polynomial degree, in order to determine how they are different. So sorry about my reminders. Another table, which is table 4 and 5, and it has to be in the next table. So we compare the depth camera with the CMOS camera, and we can see that depth camera can perform very well, and we used actually LiDAR as a ground truth because it has more precise results, and we can compare depth camera and CMOS camera, so we can see from both tables that depth camera performs better. The last experiments which we had is here aggregation of trajectory from depth camera, 2D LiDAR camera, and CMOS camera. So basically here we use the controlled robot mode when it is mobiling or following the object. So initially object located in 6.5 meters from the camera, and here the depth camera, here the 2D LiDAR camera, which are more showing a detailed path, while the CMOS camera has quite big distances in the coordinates, so it's less accurate. It could be less accurate in terms of determining the trajectories. So here are the combination of all three cameras, and what it does here, so initially object is located in 6.5 meters away from the camera, and then it gets away from the view of the camera to the right, to the different location or room. So when the camera reaches the point where the object has got disappeared, it then again tries to determine what's the object and tries to follow it again. So that's the way how we experimented. So the main objectives of the study was to implement the method for object trajectory estimating, the ROBOVIS-3 object detector algorithm, and 2D laser rangefinder. We also analyzed different models with deep learning. We also played with different data sets. We combined VOC 2007 and 2012 in order to get 12 different classes like airplane, bicycle, bus, car, cat, cow, dog, motorcycle, person, horse, sofa, and train. We trained on NVIDIA, so it was quite fast with YOLO V3. We used also Google Open Images dataset, and for running the Pascal VOC, it took us 5 days with ImageNet backbone that contains 53 convolutional layers, while 2 days it took for tiny version, which we're trying to say that here. So the tiny version of YOLO V3, also with ImageNet backbone, which contained 15 convolutional layers. So we did these all comparisons, and the results are published in our paper. We also used pre-trained convolutional weights to increase the capability of the model to detect the object. The combination of 2D LiDAR in trajectory estimation was used, and we also did several comparisons with other cameras, which are depth camera, CMOS, and LRF. We, at the last point, did the comparison, we did the experiments of controlled robot mode. And we used also polynomial regression in order to make our trajectories smoother. The experiment showed that the approach is feasible and robust to obtain the object location and further draw the trajectory. As a future work, we plan to investigate different algorithms for the object trajectory prediction, as well as methods related to object tracking using mobile robot control. So, thank you for your attention. If you have any questions, you can ask, I guess, now.